Okay, so this is the vector functions. Okay, and we have all this for R. Now we want to find the tangent plane traced by this vector at a, so suppose that observe one point, which is a point, let's say u0 and phi0. This is the one that we are going to apply to find our tangent. And there will be two possibilities. We can have a constant u, and then change in v, and then constant phi, and then change in u, which we can immediately recall this in partial derivative. If you remember the partials, we can have these two definitions, and we say that partial derivative with respect to x, partial derivative with respect to y. Now we do the same thing with this uv. So then I will write the conclusions from these two possibilities. Then we can write, suppose that we have R, and then we partially derive with respect to, let's say, phi. This becomes partial v, and then plug in the point, which is the u0 phi0. That is the one that we want to observe. So partially derive all the terms with respect to v. And then similarly, we are going to take the constant u, or partial derive with respect to u, then the v is constant. So this will be partial u, and write the same, but we partially derive with respect to u. Okay, now we have these two, and remember that this two is, we call this as a tangent vector, and if the cross product between these two, so if we cross these two, Ru cross Rv, if this is never going to be zero, then we say surface S is smooth. Okay, smooth. Which means, if you remember, what is the result of the cross product? Is the right-hand rule, right? So you have, for example, x, y, you have z-axis, right? So which means, for every point along this tangent vector, when we cross the product, there will always be a normal vector. Okay? So if we have all the normal vector, then we say the curve or the surface, it's all have like, if you can imagine like maybe a ball with a needle. Okay? Every part of it is, we call smooth. If this is zero, then at some point there will be a point that we don't know whether it's going here or here, because the point is getting all possible. Right? We can have this, or that. But if this is never going to be zero, then we say, okay, it's smooth, right? Okay, and then the tangent plane, if you see from here, the tangent plane is basically the one that is going to be having these two components, okay? Okay, maybe not really good, but imagine that maybe I will draw in dot. That is perhaps our approach approximately for the tangent plane. So tangent plane will be at least having have two component, which is RU and RV. Okay. This is basically your calculus 2. Usually we have the partial x partial y for the tangent plane, right? And then we have the normal vector for this tangent, supposed to be like, for example, maybe here for this point. This is the normal vector at the point P0. Okay. Normal vector at P0. Okay. Because if you change the point, then the vector will be changing. The normal will be changing according to the plane. So the plane will be also moving, the normal also moving. Okay, now that's the idea. So the cross product, maybe this is just a conclusion here, is a normal vector to tangent plane. Okay, now we need to start out from this a tangent plane and a normal vector, because we want to develop a definitions, okay, throughout the chapter. Okay. Now we move to what we call as the surface area. Okay, this is also part of calculus 2. This is just an overview, so I will make it real quick. So if we take, for example, in terms of the UV, we take the projections and we slice up this rectangle. We say we have a delta U and delta V, and then this basically based on this R, transformation R, that this is practically the same rectangle here that is projected to the UV. Okay? So we can make the let's say this is called the patch, okay? Or let me write the definition. Basically, this is just the calculus 2, okay, with some additional contents. So basically, if you have a smooth surface, smooth parametric surface, and we call this using R, and then the S is covered in range throughout the domain, then the surface area is basically, this is basically the area of the parallelogram. If you remember, parallelogram can be also traced by vectors, if you remember that. And then basically this is say that the double integral for the domain, the D, cross product of this, RU cross RV, and then dA. And we have defined RU and RV as in the previous statement. So this is basically saying that how we could make it into the formula. I don't want to make like write some long details here, but basically this is the one that we can trace back into if you remember the calculus 2. And then also, if you remember, if we take the x and y axis, suppose that we have the Rx and maybe this is not really, so this is x, but this is cross product with Ry. Okay. So if we took this means in terms of, or maybe let's cross product first and then take the magnitude. If this is crossing this, so if we take the determinant, so this is 1, 0, oh, I need to define, I forgot to define the functions. Let me define the function first. So suppose that z is function of xy, and then Rx will be I plus dou f dou x k. This is just taking by implicit, and this is j
plus dou f dou y k. And then if we take this Rx cross Ry, so this will be I j k, so 1, 0, and dou f dou x. From the implicit, this is 0, 1, dou f dou y. And take the determinant, and we get that this will be negative I, negative j, and then plus k. And then if we take the magnitude value of it, you will see that we are going to arrive at, this will be squared, and then square of this, and then the k will be just 1. Or this is just 1 plus, we can write as z. And this is something that we have also learned from the previous surface area. So this is basically the area of the surface. Okay. Okay. Now, from all those introductions, let's move to what we call as the surface integrals. Okay. Okay, now we define the surface integrals from the parametric surface. So suppose that we have R. Let me just rewrite again. And we are going to use UV. This is parametric surfaces. And suppose that the UV is in domain. And assumptions, the domain will be the parameter will be a rectangle, like this picture here. And we subdivide into sub-rectangles with dimensions of delta U, delta V is precisely the same with the previous picture. And then we see the surface basically projecting this to UV axis. Okay, and then we evaluate each one of the point here. So let's write evaluate f at the PIG asterisk, which is this point here. So each one of them we evaluate and then multiply by the area delta S. So we have a sum, and then this will be a function multiplied with the delta of S, the area. Okay, this means the area. So the height and the area. And then we take the limit, like in this part here. So we take limit as this sub-rectangles getting larger, if you cut into a lot of rectangles, we're going to see that the M and N is going to be larger and supposed to be getting closer to like infinitely large. So basically that is what we call as a surface integral of a function xyz with respect to ds. So this is the name of, we call this a surface integral of f over surface S. And how to understand the ds or delta s is basically from the approximation we have from the previous one. So the parallelogram with the cross product, that is going to be our ds or delta s. So we can approach the delta s approximately. This will be the cross product or the magnitude of the cross product Ru cross Rv, and then multiply with the delta U delta V, where the Ru is partial derivative with respect to U. So it means that the U and V can be any parameter. Depends on conditions. It could be perhaps if you learn sphere, you have two type of angle. You have the theta and phi, and you can also use that as well. So these two are, this is the tangent vectors, right? Tangent vectors at corner of the S. And if components are continuous, Ru and Rv are non-zero, and non-parallel. This is also important because if it is parallel, then we don't have any tangent plane, right? And then we can also write the surface integral as this. Okay? So surface integral
of f x y z ds we can write as a f at certain point of the vector functions at uv multiply with the magnitude value of the cross product Ru and Rv and dA. And notice that this is, because I already told you before, that could be also our normal vectors. Later we could also change to normal, but we can have that at a later stage. Now we can also observe that if we have, suppose that the function is a constant one, okay? If the function xyz is equal 1, then the surface integral of that 1 ds will be double integral, and this is just 1, and then we have directly Ru cross Rv magnitude, and then dA, which is basically, this is just the area of the surface, right? So we can convert the or compute the surface integral by convert it into double integral with the parameter domain D.
just one example, at least to show you how this works. But I will start with the example one here, which has we call the sphere coordinates. Okay, sphere coordinates. Sphere coordinates is a 3-point coordinates, which is comprised of the radius, then 2 angles. Angles theta, which is on the xy plane, and angle phi, which is on this z axis, and then it will be moving only 0 to pi. But for theta, it can rotate full circle. So we need to describe what will be the x and what will be the y. So if you see, because the radius is 1, so we could set that this rho, which is this radius of the sphere, this is 1, and then we could trace all the angle and all the value for converting the x, y, and z. Okay, I will write the final conclusion, but I hope you can trace back by yourself. Just using the triangle and then take 2 components, cosine and sine. Then you will have the x will be sine phi cosine theta, and y will be sine phi sine theta, and z will be cosine phi. I think for z you can see clearly from this side here. The radius is 1, okay? And the angle phi will be only from 0 to pi, but for the theta, it could be from 0 to 2 pi. So we can write the RUV, okay, with the phi and theta. So sine phi cosine theta, this is for the x-axis, plus sine phi sine theta for j, and then plus cosine phi for k. I think in your calculus too, you don't get the sphere, right? So I think I will review a little bit, okay, about sphere. But hopefully, what we need is, we need only the conversion factors and how we understand the angle, okay? And that's it. Okay. The important point for the sphere. In your calculus too, it's supposed to be having the multiple integrals, basically triple integrals, because you have radius, phi, and theta. So you have 3 variables, like in x, y, z, right? Okay, so next thing is we take the r phi cross the r phi, or let me write r phi. So this will be cosine phi cosine theta plus cosine phi sine theta minus sine, I think if I write this all to, will be, the time will be gone. So let me make it fast. sine will be 0, right? Okay. So we are going to cross this. I will skip some process here, but I think I will just write down the determinant and skip the computations. But I hope you can compute this as well. So I, j, k. This will be cosine, and then cosine, sine, and minus sine phi. Minus sine phi, sine theta, sine phi, cosine theta, and 0. And then solve this, and you get some results. But I will just write directly to the magnitude value of that. This will turns out to be sine phi at the end. But there will be a lot of calculations. But you will see some cancellations and some using identity as well. Okay, so the questions is this surface integral. So surface integral x squared ds, we can change into the x is sine phi and cosine theta, right? So sine phi cosine theta squared. And then the s, we can exchange to the cross product, and then the a. This will be sine squared phi cosine squared theta, and the cross will be sine phi. Usually we wrote the phi and then the theta, but if you switch the order, it should be okay because we are evaluating with a constant. So 0 to pi, 0 phi. And then we see that this is phi. I will make it into another. So I will separate, becomes 2. So the first one is the theta, which is cosine squared theta. I will transform into half plus cosine 2 theta over 2. Okay, this is the cosine. And then the second one is the phi. I will change the sine squared with 1 minus cosine squared. So we have sine phi minus sine phi cosine squared phi. Multiply with this sign, it becomes this, and we evaluate. And practically, after you get this, you can turn into your calculator and solve eventually. But it will end this is 4, this is 0 to 2 pi, and multiply with, this is negative cosine, and then this will be plus 1 over 3 cosine cube phi, and then plug in. I think you can just use the substitutions. Okay, you can substitute the cosine squared, and this will be 4 pi over 3. Okay. The important thing is to get the conversion with the first statement. Okay, this is the important one. The rest is, we can compute that just using the integral. Okay, that will be example 1. But I hope you can try to sort out the cross product. Okay, just make it more familiar. Take the determinants. It will have a long, but some of it will be cancelled out, and you can also use identity on the trigonometry. Sine squared plus cosine squared equal 1. There will be some of the identity, and you can cancel. Basically, you will end up with the square of the sine squared. That's the end steps, and then you can make out the sine phi. Okay. I think we have a little bit time here. Just one note that still related to the previous one. So any surface, let's say surface S with equation, suppose that we have z, let's say g of xy. Okay, we can write a parametric. So we can write a parametric surface. Let the x just x, okay, y is just y, but for z it will be g of xy. Okay, this means x is in the parameter. Okay, so we have two parameter xy, like in the partial derivative, but we are regarding z in these two functions. So for the Rx, we have I plus, I think we have done this previously, but I will write again here. This will get you to, okay, and then the Rx cross Ry, based on the cross product, we're going to have and then plus k, and then take the magnitude value, this will be n plus 1. So we can regard this, if we have the surface integral in terms of x, y, z. If this happens, we can change the z to the function of two variable x1, and basically wrote down this. Okay. So basically the idea is we need to find the partial x, partial y. So suppose that we have a function. We can have the partial x and partial y from the z. We input into the equations, and then we have the questions here, and then we solve the integrations. So basically solving the double integral. So for example, if we have the surface, it's quite simple. Double or surface integral y ds, and S is the surface of this z equal x plus y squared. So notice that we can directly get the dou z dou x, which is 1, and dou z dou y, which is 2y. And we can just plug in these terms into the equations and then solve the whole system. Okay. So basically, we can say that this is the f, right? So basically, we can write down dy ds is d, and then this is y, and then wrote the long square root for that. So this will be 1 squared plus 2y squared, and then plus 1. Okay. And then dA. And notice that we have the constant for x and y as well. So we are given. So basically we are going to evaluate either dy dx or dx dy. I will write maybe dy dx first. So this is 0, 1, 0, 2. Depends on what we have in the integrations. Then we can this is 2 plus 4y squared. This will be dy dx. And since this is a constant and we can separate this and there's no x inside, so I think we can separate by taking the 0, 1 dx and 0, 2 y 2 plus 4y squared dy. And since there will be a lot of integrations, some of the simple integrations can be easily integrated using just calculator. But my suggestion is, if there is something that you need to have some techniques to solve, then solve that using the techniques, and then after that compute using calculators. This is just to avoid some mistakes or perhaps some algorithm mistakes in your calculators. So this will be just 1, right? So we can just focus here, which is going to be, we can let the 2 plus 4y squared as u. This will be, or perhaps we can directly input. One plus okay, so you can exchange this, and this is supposed to be equal to 13 over 3 square root of 2. Okay, basically you can change that. So from y0, u will be 2, y is 2, u will be 18. So basically change to this and you get this. Okay, so that is for today's class. So we are